Hey guys, welcome back to CCL Biology, the channel for easy to understand biology lessons. And if you're new to this channel, then welcome. If you are a high school student who's looking for some help with your general or AP biology class, or even if you're a college student taking an introductory biology course, this is the place for you. I am your friendly bio nerd. Thank you so much for tuning into my channel. In today's video, I'm going to be talking about valence electrons. So if you want to get a better understanding of valence electrons, then stay tuned. While you're here, please hit the like button below if you find this video to be helpful. And if you want more easy to understand biology lessons, then be sure to subscribe to my channel and click the notification bell to be notified about new videos that go up every week. Okay, as I said, we're going to be talking about valence electrons in this video. We're going to take a look at what they are and what they do. So let's go ahead and get started, and let's start with that second topic of what valence electrons do. Valence electrons participate in chemical reactions. Okay, so let's take it back to some basics and talk about what a chemical reaction is. A chemical reaction is an interaction between atoms in which electrons are shared or transferred between those atoms. So chemical reactions occur at the atomic level, which is the basic unit of matter. So living things are organized in what's called a hierarchy. You've got atoms, which go to molecules, to organelles, to cells, tissues, to organs, yada, yada, all up the chain, okay? But chemical reactions occur at that lowest basic level, the atomic level, okay? Some chemical reactions create bonds by bringing two atoms together. So they come together because of a chemical bond in between them. And then other chemical reactions take atoms that are bonded together and they break the bond that's between them. So why do chemical reactions occur? Well, to answer that, we've got to look more closely at atoms. Now, I go into depth about atoms in another video, and I'll post the link to that in the description box below. But atoms have particles inside of them called subatomic particles. And three of them are protons, neutrons, and electrons. Electrons, as you can see here in green, are the particles that are directly involved in chemical reactions. Now, the electrons swirl around in what are called electron shells inside of the atom. So those are represented here by these two black circles. Those are the electron shells. Now, the number of electron shells in an atom is going to depend on how many electrons that atom has. So that means that different atoms have different numbers of electron shells. Some have only one shell, some have 2, 3, 4, 5, 6. But whatever the outermost shell is in that atom, whatever the outermost electron shell is, that's called the valence shell. And the electrons that are sitting in that valence shell are called valence electrons. So let's look at some examples here. Here we see the fluorine atom. Okay, and it has two electron shells. So this second shell would be the valence shell, and there are 1, 2, 3, 4, 5, 6, 7 valence electrons in that valence shell. And then if we take a look at chlorine here, we see 1, 2, 3 shells. Okay, so this third shell is the outermost shell, so that's going to be the valence shell. And there are 1, 2, 3, 4, 5, 6, 7 valence electrons in this chlorine atom as well. Valence electrons are the electrons that are mostly responsible for chemical reactions. That's because these electrons are farthest away from the nucleus of their atom, which is positively charged. The nucleus is positively charged because of the protons inside of it. So the electrons that are closer to the nucleus are pulled in toward that nucleus because they're attracted to the positive charge that the protons are giving off. But the valence electrons, even though they're also attracted to that positive charge, are far enough away from the nucleus that they can be transferred from the atom in which they're currently sitting to another atom. But now the question is, why would valence electrons want to leave their atom? Why would any atom be willing to give away their electrons or pick up electrons from another atom? That's because atoms want to be in a very stable, the most stable, relaxed state that they can be. And to get there, they need to have the maximum number of electrons in their valence shell. So they need to have the maximum number of valence electrons. When a valence shell has the maximum number of electrons in it, then that valence shell is full or completed. And at that point, the atom really has no incentive to release any electrons or take in any electrons. So it's not going to take part in any chemical reactions. So an atom with a full valence shell is considered unreactive or inert. So let's take a look here at the periodic table of the elements. If we look here, we see that each of the elements, we see these elements here in the right-hand column, and each of these elements here on the right-hand side have complete valence shells. So all of these atoms are unreactive. They're not going to be forming any chemical bonds with atoms of any of the other elements in the table. Well, how do we know when the valence shell is full? There's a set maximum number of electrons that each valence shell can hold. The maximum number of electrons that the first valence shell can hold is 2. So let's take a look at helium, for example. So here's a picture of a helium atom. It has one valence shell, one electron shell. So by default, that's going to be the valence shell. And that valence shell has 2 electrons here illustrated in blue. It has 2 valence electrons in it. So because the first shell can only hold 2 electrons, this shell is complete, which is going to make helium unreactive. So if we go back to our periodic table, we see helium here on the right-hand side. Now, all the subsequent shells after that first shell can hold a maximum of 8 electrons. So that means that all of these elements here on the right, besides helium, of course, have 8 valence electrons, which is why they're considered complete. All of the other elements in the periodic table have fewer than 8 electrons, which makes them incomplete. So to get a complete valence shell, and in the case of hydrogen, this would take only 2 electrons, not 8. But to get a complete valence shell, these other atoms have 2 options. They can pick up electrons from the valence shell of another atom, or they can release electrons from their own valence shell. So those are the 2 things that they can do to get a complete valence shell. And this is called the Octet Rule, the gain or loss of electrons to complete the valence shell. So atoms will pick up or give away electrons to get a complete shell. So even though that first valence shell, like we said, needs only 2 electrons to be complete, it still, falls under the Octet Rule. I know octet means 8, but even that first valence shell, it needs a maximum of 2 valence electrons, but that still fits under the Octet Rule. All right, so remember I said that an electron will either pick up an atom will either pick up electrons from another atom or give away some of its own electrons. Now, how do we know which option the atom is going to choose? Is it going to pick up electrons or is it going to give electrons away? Well, that's easy. Whatever choice is easier. All right, so whatever option gets that atom to a full valence shell faster and easier and quicker, that's the one that the atom's going to go with. And that's because, as I like to say, you'll probably hear me say in a good bit of my videos, is that matter is pretty lazy, all right? It doesn't like to do more work than necessary. So let's take an example here, and I'm going to draw a fluorine atom. Okay, so we'll do green to show the nucleus of the atom. And fluorine has 9 electrons total. So it's going to need 2 electron shells. So let's go ahead and draw that. So here's electron shell number 1 and electron shell number 2. My circles have never been good, so bear with me. So with those 9 total electrons, so I'm going to have 1 electron here, 1 there. So those are the first 2 electrons, and those go in the first shell. Now again, the first electron shell can only hold 2 electrons. So this shell is full, it can't take any more. So the remaining 7 electrons are going to have to go into this second shell. So I'm going to draw those in. So I've got 1, 2, 3, 4, 5, 6, and 7. All right. So the second shell is the valence shell, and fluorine has 7 valence electrons. So that means to become a complete valence shell, fluorine needs just 1 more electron, just 1. So it's really going to try its hardest to pick up an electron from another atom. But why would another atom give up electrons if it's also trying to complete its own valence shell? Well, if the number of valence electrons that the atom currently has is closer to 0 than it is to 8, then the atom would rather just chuck those electrons rather than trying to grab, 5, 6, or 7 electrons from another atom. Giving off electrons releases energy from the atom, while picking them up, having to take them from another atom, requires energy to be put in. So remember, I said that matter is lazy. So if it has the option to give up electrons and release some energy in the process, or take in electrons and have to take in energy to do that, which option do you think it's going to go with? Exactly, it's going to release energy by giving some of its own electrons away. Okay, so now let's draw a lithium atom. I'm going to use green again for the nucleus of my atom. Now lithium has 3 total electrons, which means it needs 2 valence shells. So just like fluorine, it has those 2 valence shells. The first 2 electrons are going to go in that first shell. That's going to fill the first shell up. And then the remaining electron is going to be in the second shell. So the second shell is the valence shell, and this 1 electron is the valence electron for lithium. So to complete this valence shell, the lithium atom would need to find 7 more electrons from another atom. That's a lot of work, okay? But there is another option. If we just got rid of this 1 lone electron here, so I'm gonna put a red X on it. If we just got rid of that 1 lone electron, now this shell would become empty. And an electron shell that doesn't have any electrons in it is really not a shell at all. The first shell is now going to be the valence shell. So the first shell, which is now the valence shell, has 2 electrons in it. So now these 2 electrons here, 1 and 2, now they are the valence electrons because we've gotten rid of that third one out there. Well, guess what? The first shell can only hold a maximum of 2 electrons. So this shell here, this first shell, which is now the valence shell, is complete. So that means that lithium will no longer have to go through the work of reacting with another atom if it could just find some atom somewhere that needs just 1 electron that will take its third electron. Oh, well, looky here. Here comes our friend fluorine. So these 2 atoms come together and each atom has just what the other needs. So just to keep up with the pace, the Li is the lithium atom and the F is the fluorine atom. So if they come together, the fluorine, remember the fluorine needs to pick up just 1 atom. It has needs to pick up just 1 electron. It has 7 valence electrons. It wants 1 more. The lithium has 1 valence electron and it wants to get rid of it so that it can just use its first shell as its complete valence shell. So what else is there for these atoms to do but just come together in perfect harmony? I mean, it's just wonderful. So the lithium is going to transfer its electrons over to fluorine, or transfer its 1 electron over to fluorine. And that, my friends, is a chemical reaction. You had a transfer of electrons from 1 atom to another. That is a chemical reaction. All right, so that's valence electrons and the role that they play with chemical reactions. But I do want to give one final note here. Let's look again at fluorine. Okay, I'm going to draw it again. So now I'm going to draw in my blue electrons again, and I want you to pay attention to how I'm drawing in the electrons. So I've got 1 here and 1 there. So as electrons fill up their electron shells, they don't immediately pair up. Okay, so you're going to get, so there are 7 electrons here in the valence shell, so you're going to get 1 there, then you get another one over here, you get a third one there, and you get number 4 there. Okay, now only when all of the empty space is essentially occupied by 1 electron then the rest of the electrons will start to pair up. So you'll get 5, 6, and 7. Okay, so I didn't draw them in as 1, 2, 3, 4, 5, 6, 7. They come in as 1, 2, 3, 4, then back again to pair 5, 6, 7. So unless an atom has a complete valence shell, it's always going to have 1 to 4 unpaired electrons. So as we see with fluorine, there's 1 unpaired electron here. Because remember, complete valence shell, it's going to have either 2, and you'll see that first valence shell, honestly, you'll see it drawn in 2 different ways. I have my 2 electrons on opposite sides. Sometimes that second electron will be paired right next to the first one. But definitely for the second, third, and further on shells, they're going to fill up where it's 1 here, kind of in the corners. I mean, I know a circle doesn't have corners, but you get that idea before they start pairing up. So that means there's always going to be between 1 and 4 unpaired electrons in an atom that does not have a complete valence shell. So the unpaired electrons are really the main ones that are going to take part in a chemical reaction. They're going to be the first ones. If that atom is trying to release electrons, they're going to be the first one to go. And then it's going to, the rest of the electrons are going to be released kind of in the order that they filled up. So it would be this one, and then this one, this one, this one, and then the pair, and the pair, and the pair. And if an atom is trying to take in electrons, then the first electron that it takes in is going to pair here with this unpaired electron. Well, that's it for today's video. I hope it was helpful for you. If so, then please let me know by leaving a thumbs up in the comment section below. And if you have any remaining questions, then type those as well in the comments, and I will do my best to provide you with an answer. Thanks again so much for watching CCL Biology. That is Christ-Centered Life Biology. God bless, and bye-bye.